Very good evening, everyone. Welcome to our 21 days masterclass series on autonomous vehicle. Today is day 20. I hope you're all doing well and had a productive day. I hope I'm audible right now. Yeah. Very good evening, one and all. I welcome you all for engage your learning experience with pantechelearning anytime, anywhere, at any places. We are always supporting to the students in a technical way. And our main vision to help the 10 million students easily learn the technology. So let's get into the session. Today we are going to talk about the one interesting topic, that is a motion planning in urban environments using a dynamic occupancy grid map. So first, what is this urban driving environment? What is this urban driving environment? So basically, this urban driving environment are characterized by a traffic or a pedestrians or a cyclist or any various obstacles. So these roads may have a multiple lanes and intersections and traffic signs and also the signals. So next one, motion planning. So this is the process of determining the sequence of actions. That means trajectories. So trajectories in the sense that is a sequence of actions for a vehicle to reach its goal while avoiding any obstacles in that environment. So basically this motion planning involves generating the safe and efficient trajectories for the vehicle to navigate through the urban environment. So next one is the occupancy grid map. So this map, it divides the environment into a grid of cells. So where each cell represents a occupancy of any obstacles in that road, and this occupancy grid maps are commonly used in robotics for the environment representation or any obstacles detection. So that is why we use this occupancy grid map. So these are continuously updated based on the sensor data to moving any obstacles. So next one is the freenet reference path. So this is the main thing. Today we are going to discuss about this one, freenet reference path. So what is this freenet reference path? So it's one kind of the parametric representation of the desired path for the vehicle to follow. So it consists of the two components. So what is the two component? This freenet reference path consists of the two components. One is the longitudinal, another one is the lateral. So longitudinal in the sense that is the S, lateral in the sense that is the D coordinates. So this longitudinal coordinate, it represents the distance along the path, while the lateral coordinate, it represents the lateral offset from the path. So mainly this reference path are particularly useful for the planning the sequence of actions, that means trajectories, that is related to the reference path. So additionally, dynamic replanning also involves this step, that is this dynamic replanning continuously updating the vehicle's trajectory based on the evolving environment. So this may include updating the occupancy grid map and re-estimating the vehicle position and re-estimating the vehicle's orientation and generating the new trajectories or new waypoints to avoid any obstacles and reach the goal. So that is why we use these dynamic replanning. So this MATLAB, it provides several toolboxes, particularly for motion planning in urban driven environments. So first one is the automated driving toolbox and sensor fusion and tracking toolbox and navigation toolbox also. So by integrating these toolboxes and concepts, you can develop your own algorithm, especially for the autonomous vehicle, to navigate safely and efficiently in the urban environments. So mainly we are going to discuss about this example. So we explore the dynamic replanning for the autonomous vehicle using a local motion planner. So this local motion planner is responsible for the generating an optimal trajectory based on the global path. That means that information about the surrounding. So this information about the surroundings can be described in two ways. One is the discrete set of object, another one is the discretized grid. So this discrete set of object, it representation of the environment using a discrete set of object with some defined geometries. So each object here, it is characterized by its position and also the shape and the other relevant attributes. So next one is the discretized grid. So alternatively, this environment can be represented using a discretized grid. So where each cell in the grid that indicates whether it is free or occupied. So this grid-based representation that is allowed for efficient collision. That is why we use this two ways of exploring the dynamic replanning method, and especially the autonomous vehicle. So now we get into the example. So before we enter into that, I am going to give the simple introduction to the freenet and dynamic. So basically, as I said earlier, freenet reference path, it's a imagine the road as a line that curves and twists. So this freenet reference path that helps a car follow this line smoothly. So it tells the car or a vehicle or a ego vehicle how far it is from that road and where it should go next. So making the driving easier in a tricky areas. So at that time we use this reference path. So next one is the dynamic occupancy grid map. So this is like a map the car uses to see what's around it. So it shows where the things are, how fast they are moving like that. So this helps the car avoid any collisions or avoid hitting anything in its way. That's why we use this freenet reference path and also the dynamic occupancy grid map. So now I'm going to open the MATLAB software here. Yeah. So first we have to set up a scenario. So first we have to set up a scenario. For that, here I am using the RNG of 2020. So this is one kind of the seed. So this sets the seed for the random number generated to the value 2020. So it's setting a specific seed that ensures the random numbers generated by the code will be the same each time it is run. So next we have to create a scenario for the ego vehicle and also the simulated LiDAR sensor. So for that we are using the helper grid based planning scenario. So this is like a function that is given by the toolbox and it sets up a simulated scenario with an urban interaction and creates a ego vehicle and simulated the LiDAR sensor. So that is why we mentioned that one. So basically this helper grid based planning scenario, it's one kind of the function to the three variables. So what is the variable? Scenario, ego vehicle and LiDARs. So these variables will be used later in this code to interact with the simulated scenario and also the sensors. So now I am going to set up the configuration for each LiDAR. So for that we use this line here. So sensor configuration. So sensor configuration in the sense this is one kind of the variable. So this variable will hold the configurations for each sensor. So this cell, inside this cell, we use a Newman and of LiDARs of 1. So this creates a cell array with a size equal to the number of LiDAR sensors and each cell initially empty. So that is why we mentioned that one. So next we are going to fill in the sensor configuration and this loop iterates over each LiDAR sensors and filled in the corresponding sensor configuration. So using this helper get LiDAR configuration function. So this helper get LiDAR configuration function, it's likely retrieve the configuration parameters for each LiDAR sensor based on its characteristic and based on the ego vehicle properties. So next we are going to set up the tracker here. So inside this tracker we mention so this block of code, it sets up the grid based tracker using the tracker grid RFS system. So this is the tracker grid RFS system. So inside this function, we specify the sensor configurations for the tracker which were previously defined. And next one is the has sensor configuration input That means true. So it indicates the tracker takes a sensor configuration as an input form. So next one is the grid length and grid width and also the grid resolution. So these parameters, it defines the grid dimensions and also the resolution as well as the local origin of the grid. Next one is the number particles and also the number birth particles. So these parameters, it controls the number of the particles used for especially the tracking and birth of the new objects. So next one is the velocity limit and birth probability and also the process noise and death rate. So process noise in the sense, it defines the process's noise covariance matrix for the tracker. Next one is the death rate. It sets a rate at which objects to be disappear. Next one is the free space count factor and it specifies the discount factor for a free space, that means empty grid cell. So next all the parameters that is related to the object association and also the clustering. So this it set up the configures for the grid based tracker with various parameters to effectively track the objects in the urban environment. So next we are going to set up the motion planner here. So what is this motion planner? Inside this motion planner, what we do? We specify the waypoints. So basically this waypoints variable, it contains the list of the waypoints that define the global reference path. So here each row, so this 110.6 and minus 4.5 and 0. So each row, it represents a waypoint where the first two columns are the x and y coordinates. And third column is the angle, that means theta, orientation angle. So next we mention the reference path. So this variable, it holds a reference path object that is created using the reference path freenet. This is one kind of the function from the navigation toolbox. So this function, it constructs the freenet reference path using the provided waypoint. So this is our waypoints that enabling the vehicle to plan the trajectories that is related to that path. So finally, we are going to visualize our reference path. So this block, it visualizes the reference path within the urban scenario. So that is why we create a new figure window. So this figure, it holds the handle to the figure window that is created for the visualization. And next one, we mention the axis. So this variable, it holds the handle to the axis within that figure. Next, we create the plot. So inside this plot, we mention the scenario and parent and AX. So this command, it plots the urban scenario within that axis. And next one is the show function. So we use this show function. So this command, it overlays the reference path onto the visualization. So next one is the x limit and also the y limit. So x limit, it should be minus 122.80 and y limit, it should be minus 162.40. So it sets the limits for the x and y axis to provide a viewing window. So suitable viewing window for the scenario and also the reference path. So this is the output of that one. So later I will show you the overall output. Here we use the snap now function. So what is this snap now function? So basically the snap now function in MATLAB that is used to take a snapshot of the current figure. So it captures the current state of the figure, including all the plotted elements and all the vehicles, and save it as in a new image file. So that is why we use that one. So next we are going to create the sample local trajectory. So in this step, this algorithm, it generates a set of the waypoints, set of the sequence of actions that the vehicle can follow in the local environment. So in driving scenario designer app, we manually create the waypoint. But here we are using the one algorithm that is the freenet reference path algorithm. So that algorithm, it automatically generates a set of waypoints, set of the trajectories. That means a sequence of actions. The vehicle should follow that one in the local environment. So this can involve some different trajectories. So considering the various factors like the speed or a distance along the reference path and the curvature. So that is why we use this sample local trajectories. So we are going to find the feasible and collision-free trajectories also. So once the trajectories, that means sequence of actions, are sampled in the sense, that algorithm evaluates each waypoints to determine if it is feasible and also the collision-free. So feasibility can be assessed based on the factors such as the vehicle dynamics and road and adherence to the traffic rules. So collision checking. So collision checking also is performed to ensure that waypoints do not intersect with any obstacles or do not intersect with in front of the vehicle also. So again we choose the optimal criteria and also we select the optimal trajectories also. So after evaluating the sample trajectories, this algorithm, it selects the optimal trajectory based on the predefined optimal criteria. So throughout this step, this local motion planning algorithm, it uses to create the sample trajectories and assess the feasibility and collision-free condition also. So now I am going to do that one. So that is why we create the connector. So this connector is one kind of the new variable. Here we use the trajectory generated freenet function. So this is a function from the navigation toolbox in MATLAB. So it creates a new trajectory, that means a sequence of action generator, object for the planning local waypoints in a freenet coordinates. So again we are going to use the reference path. So this variable, it contains the reference path that was previously defined. So this trajectory generator will use this reference path to generate the local trajectories. So time resolution should be 0.1. So it specifies the desired resolution in time for the trajectory. So it determines the interval at which the trajectory generator will sample points along the trajectory. So we mentioned the 0.1. So again, we are going to visualize the path regions here. Yeah, so visualize the path region for the sampling strategy visualization. So here we create the path points. So this line, it finds the closest points on the reference path to each of its waypoints. So effectively for the mapping purpose, effectively for the mapping waypoints to their position along the path. So next we create the road S. That means it extracts the distance along the reference path that is corresponding to the each waypoint. So next one is the intersection S. So this road, this line, it identifies the distance along the reference path that is corresponding to the intersection point. So next one is the intersection buffer. So it sets the buffer distance in a freenet coordinates. So to be used in the defining the region for the particular sampling. So next we mention the path is green color. So it defines a region where the terminal states will be sampled using the green strategy. And next one is the path blue. So it defines a region where the terminal status will be sampled using the blue strategy. So next we use the hold function here. So this command, it ensures the subsequent plot commands will overlay on the existing plot. That is why we use ax here. So finally, this plot, the green region path and the axis with the green color and also the line width should be 5. And this next line is the blue region path on the axis with the blue color and line width of 5. So again also we use the snap now function. So this captures the current state of the figure. So including all the plotted elements and also the settings, and save it as a new image file. So that is why we use that one. So again here we are using a one formula. So inside this it sets a speed limit. It sets a maximum speed limit for the ego vehicle. So in this example, we set the maximum speed limit is to 15 units, 15 meter per second. And what is the lane width? Lane width should be 2.975. So it defines the width of the each lane. It represents the width of the lane where the ego vehicle is driving. So in this example, I am using the 2.975 meters. So next we use this formula here, that is a del t equal s top of 0, 0, 0. So that means it specifies the set of discrete values for the longitudinal velocity. So these predefined sets of the variable del t and s and also the d, that is used to sample the terminal states for generating the local waypoints when the ego vehicle is in the green region. So when the ego vehicle is in the green region, we want to plan how it should move in the next few seconds. So we want to plan based on this formula only. So what is the formula? Time interval. So that is a del t. So we think about how far ahead we are planning. So we divide this time into the small steps to make our planning more easier. So for example, we might plan for the 2, 3 or 4 seconds into the future. So next we decide how fast the vehicle should go. So we choose from the options like going slowly, maybe even stopping also, or going up to the maximum speeds allowed. So next one is the D, that means a lateral position. So that is why this is the D, this lateral position. So we think about whether the ego vehicle should stay in that lane or change the lanes. So we have two choices, staying in the same lane or moving to the adjacent lane. So we are all putting to all together. We plan whether where the ego vehicle should be after the del t time. So we use some special value, that is the NAN, to the figure, computer figure, how far the vehicle travels based on its speed. So we also choose its speed and we also choose its lateral position also based on the options we set. So by considering these factors, we can plan how the ego vehicle should move in the green region. So ensuring it accelerates smoothly and stops safely and staying in the lane or changes the lanes as needed. So this is the way you are going to define your path. So next we are going to finding the feasibility and collision free trajectories. So what does this mean? So this ACC maximum 15 in the sense it sets the maximum allowable acceleration speed for the ego vehicle. So it represents the maximum rate at which the vehicle can change its speed. So here I am going to choose the 15 meter per second. Sorry, 15 units per second. So next we are going to setting up the collision validator here. So inside this vehicle dimension, so we have vehicle dimension function, ego vehicle and length and also the width. It creates a vehicle dynamic objects based on the length and width of the ego vehicle. So next we use the collision validator. So this setups a collision validator object. And this validator checks if the ego vehicle can safely move without colliding with any obstacles or any vehicles in that lane. So next we specify the maximum time also. So it sets the maximum time horizon for the collision validation to the 2 seconds. It determines how far into the future the collision validator predictor any collisions in that lane. And finally, we are going to provide the dimensions of the ego vehicle to the collision validator. So by defining these values, setting up a collision validator, the algorithm ensures that this sampled sequence of action, that means trajectories, are feasible and collision free, allowing for the safe and efficient motion planning. So finally, we are going to defining the cost function here. So finally, we are going to defining the cost function here. So J is in the sense that is the it represents the cost associated with the jerk in the longitudinal direction. JD in the sense it represents the cost associated with the jerk in the lateral direction. So PC in the sense that is the collision probability that is obtained by the collision validator. And we use the S dot, that means del T. It represents the longitudinal velocity of the ego vehicle after the time interval del T. So it measures how close the vehicle's speed to the desired maximum speed limit. So based on this only, we have to calculating the trajectory cost. So this is the way you are going to create your own algorithm, especially motion planning algorithm. So tomorrow we will run this one. Before I am going to show you the output. Just a minute. So the main output of this example, just a minute. Yeah. So this is our main output. So here you can see this is our ego vehicle. So this example, it demonstrates the generation of the optimal trajectory. That means a sequence of actions for an autonomous vehicle navigating through an urban environment. So the main goal is to showcase the capabilities of autonomous driving system to safely and efficiently navigate the complex urban scenario. And this is the output of this example. Tomorrow I will show you output in MATLAB. So how this happened? How this navigation, it occurs through a series of steps. So that means perception. So the ego vehicle perceives its surroundings by using the lidar sensors, so which provide the information about the nearby objects, including their positions, including their velocity also. So these sensor data can be fused into create a dynamic occupancy grid map. So this is the dynamic occupancy grid map. So which represents the local environment around the ego vehicle. So this ego vehicle, it plans its motion locally using the freenet reference path. So freenet reference path. So this reference path, it involves local trajectories considering the factors like the speed or a time or a lateral positions like that. So each sampled sequence of actions is based on the criteria, which the factors like the jerk or a collision like that. So this is our navigation process involving continuously perceiving the environment and planning the feasible trajectories and dynamically adapting to the new changing conditions to ensure and save an efficient motion of the autonomous vehicle. So this is the output. Thank you so much.